So I have a meeting down at URI on Friday. So Majid is going to come and work through some example problems with you guys, which would be cool. And so that will be the plan for Friday, but it'll still be the remainder of chapter 8. We're still continuing on our progress towards the midterm next week. So what I thought would be useful today then, since Majid is going to be running through a bunch of examples, was just to kind of clarify what the different kinds of functions we have for vectors and scalars and how they interact with each other. So we're going to spend today thinking about that. And so I started out by making a little table. So these are things, so I have inputs across the top and outputs on the side. So if the input's a scalar, like, and I just have little lowercase a, b, and c as examples, then we would, and then if you input those and you get a scalar out, we'll put it in this box. If you input vectors and get a scalar out, we'll put it in this box. If you input vectors and get a vector out, we'll put it in this box.
Guys, one question. For the homework, it's something reminded to do next Wednesday. Is that correct?
Oh, I thought it was supposed to be due on Friday.
Yeah.
Sorry. Which version is saying that it's?
The one on Canvas.
Oh, the one on Canvas?
I'm pretty sure as of yesterday it said it was due on like.
Oh, I think I had it set up that originally, but then I got worried that we wouldn't have enough time for the midterm review. So we'll try and push it up to Friday if everybody can do it. This Friday, yeah. Because next Friday is the midterm. So
right.
That's really, if that's crazy, we can push it back into the weekend. But one, it's a holiday weekend, and two, I was hoping you guys were going to have time just next week clear of thinking about homeworks.
That's solid.
Okay. Should we do it? Do you want to do it on Saturday or Sunday or Monday? I mean, all of those are fine. I just don't want everybody to get crowded into preparing for the midterm. This one is shorter than the previous ones have been because this is a compressed schedule. Yeah, why don't we just say Monday? So you'll have access to reviewing it on Monday, and that works for getting ready for Wednesday anyway. So it's only really when the reviews kick in and when I put the answer key up that's the important thing. So I'll do all that on Monday. So homework due Monday. So it'll be the normal schedule then, even though Monday is a holiday. And you can turn it in early if you want. Okay, all right. Sorry about the confusion. Okay. All right. So let's start over here, thinking about things we already know, and then we'll build up the things that we don't know. And one of the things I want to really focus on is the fundamental theorem of calculus. Because now in vector calculus, we're going to have a lot of different flavors of them. But even before we get to the derivatives and things, what can I do with two scalars that gives me a scalar as an output? Multiplication. A times B equals C. Good. Or addition. A plus B equals C. Also good. Do we have, what about multiplication of vectors? Do we have a multiplication operation with a vector that gives us back a vector? Cross product. U cross V equals W. Vector times a scalar. So those are vector to vector mappings. And I guess this one is vector and a scalar. We can always multiply all of these by scalars in addition. Once we've got this one, we're free to multiply as much as we want by a scalar. What about vector plus a scalar? You're shaking your head. What's the problem with vector plus a scalar?
The dimensionality is small.
Yeah, you just can't do it. It's one that doesn't make sense. So, all right. What's in vector times vector equals a scalar? Dot product. So U dot V equals A. is a good example of that. What, is there another vector equals scalar, or is that the only one?
Gradient.
Gradient. So what does the gradient do?
Not the gradient.
Careful, the gradient is similar, but what does the gradient do? We take the gradient of a what and we get a what? Take a scalar and get a vector. And remember, this funny symbol is the one we talked about last time. I'm gonna write that out over here. We pretend like it looks like a vector. It's really a bunch of derivatives, partial derivatives, encapsulated in in vector form. So we can write it a bunch of different ways, but that's one of our, so in the gradient form, we're treating it like an analog of multiplication of a scalar by a vector. So we put that one over here, but maybe we should have actually put that one here. And so this looks an awful lot like that. Everybody see what I mean? Except it's not a multiplication, it's a derivative. Okay. So we got multiplication, we got addition. What about other derivatives? What other kinds of derivatives do we know how to take? So we took a gradient, that was one flavor of derivative. But are there other flavors?
We could take the divergence, which I think would be like vector becomes scalar.
The divergence looks an awful lot like the dot product. And symbolically, it's meant to remind you of that. That's totally why. What about a scalar derivative to a scalar derivative? We can take any derivative we want, as long as it's a total derivative. And then it's just scalar to scalar. Right? So this is like our old-fashioned univariate calculus world over here, living in scalar to scalar. So we're happy to continue on that front. It's a little dangerous to think of this as a scalar to scalar operation. Why is that? Is that actually a scalar to scalar operation? And by here I mean the coordinate direction x.
Like we live in three-dimensional or like three spatial dimensional worlds, so you can't actually really like move something only in.
Yeah, so this is like the component of a vector. This is one component of this operation. So this thing over here on this side is actually not a scalar. If I take a derivative with respect to one coordinate direction, that can't be a scalar. Because if I now choose to reorient my coordinate system in a different way, this thing changes. A scalar is the thing that doesn't change when I rotate or reflect my coordinate system. Remember, like we talked about on Monday. So let's not put that one in. Though that can be a valid operation sometimes, it's a valid operation when you have a particular coordinate system in mind. And you should not interpret that component of the gradient as a scalar. It is not. It is a component of the gradient. So as long as you're thinking about it that way, it's okay. Does that make sense to everybody? All right. So we had just one flavor of derivative over here. That's okay. What about integrals? What kind of integrals can we do? Oh, we're actually missing, wait, we're missing a derivative. There's one more kind of derivative that we haven't written down yet, which looks like this one. What's the derivative that looks like that one?
The curl.
The curl. So the curl is one we have barely talked about, and one of the reasons I wanted to write all this out was we can go through these and remind ourselves, or see for the first time, for some of you maybe, what all of these operations mean. Okay, so now we have a derivative that goes scalar to scalar, a derivative that goes vector to scalar, a derivative that goes vector to vector, a derivative that goes scalar to vector. So maybe that's it. It is. That's maybe not obvious. Okay, what about integrals? What's an integral that goes up here? Our normal kind of integral. Integral of a dt equals b. Sure, why not? That's the normal one. What's an integral that goes vector to vector? Maybe it's not obvious, but I claim you can integrate a vector component by component and just get another vector. So that's one. Do we have an integral that goes from a vector to a scalar? It's different from like this operation. Maybe not familiarly. So integrals are a little bit funny. So I want us to think about the integrals in a different way rather than this kind of operation sense. Even though they are linear operators, so we can push them through and they will preserve the components and the rotation, because the rotation matrix is another linear operation. So as long as you're careful about order of operations and not having funny things in the bounds, we can integrate and preserve the transformation of the coordinate system. So we could do like this, or we can differentiate and preserve the scalar quality if we're not using a component here, but we're actually taking a real total derivative here. So we can think about those. But what we really want to think about then is we want to think about something that's like our fundamental theorem of calculus. So what was the fundamental theorem of calculus? We have in the regular old way of doing it. We had integral from A to B, f of t, dt, d by dt, f of t, f of a, minus f of b, right? And relatedly, we had the Leibniz integral, the Leibniz differentiation, which was z by dt, a of t, b of t, let's see, f of t, dt. What was that one equal to? Remember? Am I doing this right? That's the bigger question. Is that right or not? I don't have it written down. I always forget the way the Leibniz one is. But we need to, if these guys depend on something, oh, sorry, I can make this a little more explicit.
also an integral in.
There's another integral in the other part too. Gosh. Alright, did I do that one right?
What is the partial of x of the function x comma t, which I'm not sure if that's involved.
Right, so this one, I didn't write it that way. And I had it as partial. Not getting closer. So, in both of these, the point is supposed to be that the derivative and the integral are inverse operations. So this one is a little complicated because writing in the form where these guys are also dependent on this function, you get these extra two terms. But if you just pay attention to this one, it's telling you that the derivative, that I can commute the derivative and the integral, and this one is saying, really, I can undo my derivative by integrating, right? This way. Okay. So, we need something like, or we might like to think about something like this for these funny derivatives. The ones that are the gradient and the divergence and the curl. So it turns out there is something that's sort of like this one, and there will also be one that's sort of like this one, but let's not worry about that one for now. That one's a little bit more tangled. What if I write something like this? So this is the gradient of something that depends on x and y. Z. And I want to integrate this thing somehow. And let's put it from A to B. Oh. A, B. Put it in the right order. And not getting little lines everywhere. Okay, so this is a gradient. So what kind of an object is this gradient? Vector. So we could just integrate it like this and see what we come up with. Integrate it in time, say some other axis that's not the thing we're worried about. And if these are independent of time, just like we did before, we will end up that we can just commute those through. So the gradient can act on the outside, the gradient can act on the inside, and there is a kind of Leibniz rule-like thing where we might have to have, if these depended on x and y and z, we'd have to differentiate those as well. So that's one thing we can do, but that's not really the equivalent of this. That's more the equivalent of like the Leibniz rule, that I can commute these guys. What I'd like to have is I'd like to have something like this to this. So let's think about a little bit about what if we have, okay, let's draw some contours here. So this is in, if I'm looking, and say x, y, I'm looking down from above on some kind of field like this, and let's say it's positive to the outside and negative to around the outside, so I'm contouring a scalar field in space. Everybody understand what I'm doing? So this is a high, and it's decreasing like this. Where is the gradient on that? How do I draw the gradient on that map?
It's perpendicular to the contours.
Perpendicular to contours. How do I see that from this formula? Let's think it through. So what's the x component of the gradient? If I look up here, we have the gradient. So this guy, the x component of the gradient is d by dx of f, right? The y component is d by dy of f. The z component is d by dz of f. So the x component is d by dx of f. So what tells me about d by dx of f here? Where is d by dx big, and where is it small?
Bigger on the right side? Are you like?
So this, on this side, with the function, so if we think of like the derivative as a slope, so we have the change in the function over the change in space. So rise over run, maybe? You know, if I was plotting it like this, I might plot it underneath, and it would go up, and then it would come down slowly. So where's the derivative then? This is like a transect through there. So what's d by dx of f?
Greatest when you have the steep change.
Greatest when you have the steep change, and slower when you have the... So the closer the contours are together means I have the biggest change in f per unit distance in x. So the gradient is bigger here than it is there, or at least the d by dx component. And if I'm looking at distances in y, the gradient is bigger when my distances in y direction are bigger, and less when the distances in s and x distances in y are bigger. Because each of these has a unit change in f. So if I think of the f dx as delta f over delta x, in between contours, delta f is the same for everyone. But the delta x is different, depending on whether the contours are close together or far apart. Okay? All right, so now we know that the gradient, okay, so that tells us where the gradient is big. The gradient is big when they're close together, small when they're far apart. Which way does the gradient point?
Uphill.
It points uphill. How can we tell that? Let's look. So df dx, the x component of the gradient here, is what? Positive or negative? Going this way, in x, increasing in x, is f getting bigger or getting smaller? X getting bigger. So the x component is positive. What about over here? F is getting what as we go this way? Smaller. So here the x component is negative, right? What about this direction? Is the y component positive? Because as we go increase in y, we're increasing in f. So the y component is positive here. What about the y component up here? As we're increasing in y, decreasing. So y component is negative there. So, okay. Now let's do one more magical thing. The gradient, we keep saying, is like a vector. So I can do it component by component, but I really should think about whether, like, if it's a vector, it shouldn't really matter which direction my components are pointing. It should only be sensitive to like the shapes that are in the problem. So I guess that when I look at a contour, I have two different directions that are important. There's the kind of in and out direction, the normal direction, and the transverse, the along direction. It could be either direction. So those are the only two directions that are important on this contour. So which one is the gradient? The perpendicular. Everybody see how that goes? So if I'm positive and perpendicular here, 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 it is indeed pointing toward the positive from the negative directions. Okay? So that's what the gradient looks like. So, how can I integrate some gradients? What are some integrals of gradients that I might want to do? What happens if I integrate, if I choose a path? Just put A and B somewhere out there in space. What? I could integrate the gradient like that. And it would be kind of summing up the different vector components as I went along. That's one thing I could do. And that would be of this flavor. That's not a special integral. That would just give us something that was like the gradient of the scalar all the way along. It'd be like the average value of the gradient along that contour. But there is something special I can do because this is a vector and because this trajectory has an orientation. What can I do instead? Rather than multiplying this by a scalar element of length, I can multiply it by what?
A vector since the path has a direction.
Yeah, so everywhere along the path, I could say, what if I am taking little infinitesimal lengths everywhere I go along? And then I have a vector increment. Then I would need a dot product to interact with those vector elements. So now I've got, what kind of an object is this? It's a scalar. And here is the fundamental theorem of calculus for gradients. The gradient of a scalar, when dotted into the length vector as I'm integrating along, gives me back the difference in the scalar values of the endpoints. So the integral cancels out the gradient, and I get back to the underlying scalar field. So does that make sense to everybody? That I sort of had to do some kind of dot product because I wanted to invert something that took a scalar and made it into a vector. I wanted to get back to a scalar. So I had to do something like a dot product to do that. And the dot product, it turns out, is the integral along the length, is the right one, and then that gives you this minus this. So that tells us something very magical about the gradient. It tells us that that particular integral of the gradient doesn't matter. Here's the crazy thing, it doesn't matter what path I took from A to B. I could have also just as well considered this little path. moving along this way. If I have a totally new definition of DL, or this one, you know, that, and then goes to B. Does that matter in this fundamental theorem of calculus or not? Doesn't. I mean, it would be very hard to calculate all these little intervals. But what this fundamental theorem tells me is that as long as the derivative operator is the gradient one, the special one that takes a scalar and turns it into a vector, and I dot it into a direction along that length, the answer doesn't depend on the path I took. So all of those integrals all have the same answer. So when you do something like this, the result is independent of the path. So the gradient is a very special operator. It is the operator that can be undone by integration and brought back to the scalar like this. I could have written some other crazy thing. I could have tried to do this one, the one we were just writing. What if I just put in the component? And then, no, I can't. Oh yeah, I can do this. If I did this and then I didn't, oh no. If I tried to do something else, where I can't even decide what to do, dt, and integrate with respect to time or something, I can't undo this derivative that way. I can undo one component at a time if I did an x integral, but I can't undo it all the components all the time, regardless of my coordinate system, unless I use this special operation. Okay? So this is why the gradient is important. It's the one that can be undone by integration. It's a special operation. It's the special operation that turns a scalar into a vector through differentiation, and it's also the special operation because it can be undone, because it has this fundamental theorem. So what are the kinds of things then that might be a gradient of something? So the fact that I'm drawing a contour map already means that I kind of had gradient in mind. Can I contour a vector? In general, like, give me all the velocities in this room. Can I contour that? Contour their magnitude. I could contour their direction as separate figures, but I couldn't put them all into one figure. So the fact that I started out with a contour map meant I was already thinking scalar, and the fact that we could draw the gradient on that contour map meant that there was already some special relationship between the gradient and the scalar field that we wanted to explore. Okay? So there were a lot of choices in the way we arrived at this thing that were kind of implicit. Okay, one more thing I want to say. Does anybody see a resemblance between this and this? Yeah. So what's the equivalent thing that's playing the role of d by dt on this?
Gradient, like the partial derivatives.
So the gradient's playing the role of the derivative, and then the dl, the magnitude of the matching of those two. So it has a little bit of a sense of a directionality. It's not the gradient in every direction, the gradient in the direction of dl. So there's a cosine of the angle kind of thing. But aside from that, this looks an awful lot like this. So one way to remember this is what we're doing is doing exactly the same operation as this, but in this instance, L is counting the distance along a particular trajectory the same way that time counts the distance of along the derivative of time. And the gradient is playing the role of the total derivative, but in but the dot product is an important part of the action of the gradient that makes these two a little different. So this is like the geometric extension of that.
So is TL like changing direction as you travel along?
It is. So every single unit GL is always locally tangent to the path. And it works for any path you choose between those endpoints. The second part is the really crazy one. And we'll see in a minute that that's not true of any, that's definitely not true of any vector dotted into GL. That is not, absolutely not the case that this is independent of path. Only this one is. Okay? Because I can do something else and build another vector that will not have this property. Okay? So the gradient is a special vector. It's not a generic vector. Okay? All right. So let's look at this guy and think about what its fundamental theorem of calculus might be. So what does my divergence look like? And now I need to draw a different kind of map. I can't draw a contour map. I need to draw a vector map. So the divergence of a vector field, I just draw some vectors randomly. Everywhere in space, I've got vectors. All right. Some of them are big, some of them are small. Some of them, they're supposed to all be straight. Okay. Just based on the name, where is that vector field diverging? Did draw a really obvious one. Maybe I should make one that's really obviously diverging. Okay. So all of the vectors are going away from this point. So they are diverging. How does the divergence actually show me that? So the divergence is what? Divergence of V, which is like a vector operation, d by dx, d by dy, d by dz, dotted into V in the x direction, V in the y direction, V in the z direction. So dvx dx plus dvy dy plus dvz dz. So we have only x and y here, so we just won't have that term. But what is dvx dx? Right, look at this point. What's it telling? So Vx is the x component of the vector V. So where's the x component of this cluster? Like, how do I read it off?
All the vectors.
Or of each one. So where's the x component of them?
It's to the right field.
So it's like, if I project down into the x direction for each of them, it would be that projection, which is small for those, but it's the x, the x projection of them that is giving us the x component. So I'm making little right triangles everywhere, and think about it. And the y component is the other one, right? That's this direction. So looking at these two vectors, the x component is what here? Positive or negative? Negative, and the x component here is positive. So what's dvx dx here? 0. Careful. It went from a negative to a positive as I increased an x. So if I plot vx by x, it's going like that. So is that a positive or a negative derivative? Positive derivative. So here I have dbx, the x is positive at this point. What about dvy, dy? This one. Here, what direction is vy for these two arrows? Down, so negative. And what about for these two arrows? Up. So it's going from negative values to positive values as I cross. So it's the same situation. So this is positive. We don't have a z component. So that says overall the divergence of this vector field at that point is positive. So the fact that it's diverging, it's going away from a point, is in fact the divergence. And if it was converging, what would happen? It'd be negative, because instead of this increasing from here to there, it would have decreased. So if this vy increasing, it would have decreased. So this thing really does reflect the divergence. Okay. So, if that's what the divergence means, what kind of an integral am I going to want to do with that thing? I could just integrate over some area around it. And if I didn't do anything special about changing the vectors into scalars or anything like that, the divergence, so the divergence is what? A vector or a scalar? It's a scalar. So the divergence from a point, then, is going to be just a scalar. So I can just integrate over this surface, and nothing special would happen. I would just have an integral of the divergence. But if I draw another field that's not diverging, and I integrate over that area, is there something that you notice about the arrows in the diverging point and the arrows in this not diverging field? What are they doing? What?
Spreading out.
So here they're spreading out. So are more arrows going out or going in? Going out. Here are more arrows going out or going in, or the same amount? The same. So there's something special if I think of an enclosing volume that has to do with the divergence. So there's a fundamental theorem of calculus which says that the divergence integrated over a volume. Everybody on board with what that means? And I could write this with 3 integrals if I wanted to make it be really explicit. It's going to be equal to the closed surface where if I take the normal direction, so the outward normal, the area is equal to an area element in the normal direction. So this one is, the divergence takes a vector operator and a vector itself, and it makes a scalar. The dot product takes a vector and it makes a scalar. This one is a fundamental theorem because this is taking a 3D integral of a 3D derivative and giving me only a 2D integral. But this, does that make sense to everybody? And what it's saying is it's saying if I integrate this scalar field, this thing, the divergence, everywhere inside the volume, I can instead have thought about the vectors themselves and how many of them tend to be poking out. And those two things are related. So this is a really powerful one because this is going to allow us to convert from stuff coming and going into a volume this way to the divergence inside that volume. Okay? So this is another fundamental theorem of calculus, which we will play with some more. We're running short on time today. One more I gotta write. So what about this little region of flow right there? What's it doing? Is it diverging? No. It's sort of spinning around in a circle. So the curl is the one that measures the degree of spinning around in a circle. So the curl, the easy way to think of the curl is that it's the determinant of this matrix Okay, so we have only x's and y's here, so I can set this one to 0. But we have to figure this out. So I go that one's 0. That one's not 0. So I have j hat dv x dz. Then I do this one, this one, this one, this one, plus k hat dv y dx. Then I go the other way. And that one minus k hat dx dy. So I put these two together because they're both k hats. And then another one, which is this one, which I'm going to, sorry, I'll erase it and write it this way. My first one is dv x z minus. And then there's plus I hat, but in this case, those are 0. Yeah?
Would it be negative j hat?
So this one is the positive one, dvx dz,
Oh, okay.
and this one, wait, sorry, this one is the, which one? This one is 0. Where's the other one that I'm missing? This one, this, oh, this one is 0, because dz is 0. So I'm still missing 1. There is 1 on the I hat, but it's not 0, which is negative, oh, it's dv y dz, but that one's also 0 because I don't have any z variations.
So the j hat is 0 too.
This one is also 0. Yeah. So this is the only one that's really important to us for this particular problem. But we could have written out all 3 and gotten all of them. So what does this guy look like? What's its direction? Its direction is k hat. So we're taking a derivative in the xy plane. Which way is it pointing? Somehow out of the board. So that's already weird. Remember we said the curl was weird. It's really fundamentally 3D. So we're taking a derivative of something in a plane and getting an answer that's perpendicular to that plane, just like the cross product was. And there's a right-hand rule for this one too, almost related to that. If you curl your fingers around in the direction of motion, the direction your thumb is pointing is the direction of the curl. So it actually is going into the board in this case. And we could go through that same exercise of saying what's the y component of those vectors and how do they change in x, and what's the x component and how do they change in y. And we would find that there was a negative curl there. So there is a curl, fundamental theorem of calculus, which looks a little bit like this one, except it's a 2D thing. I take the curl and I dot it into the area, and I get it closed. So if I take an area integral like this and dot it into I take the curl of that and I dot it into an area element poking out of that element, I'll get the integral of going around in a circle enclosing dotted into this. So if it's spinning inside everywhere, if you integrate all of the curl up, it'll be spinning on the whole domain boundary. That's what this is saying. And you can think of funny cases, like what if I have one going this way next to one going the other way, which is impossible to draw. Okay, so this one has negative curl, and this one has positive curl. So if I integrate over the whole thing, what's the sense of curl overall? 0-ish. And so you can see that if I do the integral of that flow field, I'm going this way for part of it, and then I start going backwards for the other part. So v dot dl will be 0 if I go all the way around, because part of the time it's adding up, and then part of the time it's negative. It's in the opposite of the direction. So curl is another special derivative that has a fundamental theorem. Okay? So, we run out of time on this. I'm going to send Majid a couple of things that we need to get discussed on Friday, and then we'll go back over all of this stuff again on Wednesday.